Okay, here we go. So, what we're doing here is we're putting in the data from the graph into the calculator. Okay, now, I want to be able to graph it on my calculator. Okay, because are you always going to want to have to do a graph by hand? No. So let's go ahead and set it up to graph. The way you do that is bars, y bars, function. Okay, now look, I'm going to put it in y1. That way when I go to the graph, it's already there for me. I don't have to type it in. Now I'm going to calculate it. Okay, now, you know how a linear equation is y equals mx plus b? And a quadratic equation is y equals a times x minus h squared plus k? And then we also learned the equation for an ellipse, and we learned the equation for a hyperbola. Now we're going to learn the equation for an exponential function. The equation is y equals a times b to the x power. A is your start value, sometimes known as initial value. B is your growth or decay factor. And then x is time. Okay, well, when I put in my data, they went ahead and gave me the A value and the B value. Okay, so my starting value is about 292. My decay factor is 0.81. So I'm going to write that down. I'm just going to round up to a whole number. And then my B value is 0.81. And you'll understand in a few minutes why I'm not rounding that up to 1. Okay, now, so if I write the equation in A times B to the x form, it'll be y equals 292 times 0.81 to the x power. So, now that I have an equation from my data, how can I use that to predict the time in seconds if I did it 20 times? What did we say x represents? Time. Right, so I'm going to put the 20 right there. So it'll be y equals 292 times 0.81 to the 20th power. And what do you get? I will wait a few minutes. Okay, so we'll just round it off. 4.3. So 4.3 seconds. Now, that seems a little unreasonable because at some point people are going to max out, right? But if you were to continue to improve at the same rate, that's how fast you could do it. I mean, this person achieved 25 seconds by their 12th time, so maybe 8 times more, maybe they could get that low. Okay, if they were really focused, I mean, at that point, it's just a matter of circling them that fast, because you pretty much have memorized where all of them are. You're not looking at all. Now you're probably thinking like, well, why is this useful? Have you ever seen Shark Tank and heard them ask the entrepreneur that's on the show, what are your predicted sales for next year? Okay, well that's the scenario. They take their data of sales from last year, the current year, and that's how they get that prediction. Okay, this is used all the time in jobs. Okay, you have to be able to predict the future for companies because otherwise that's how companies go out of business. Okay, if they're not smart and they don't predict well, then things can go downhill fast. Okay, so now another thing you can do with the calculator is we can see the graph. Let me make sure it's turned on right. Okay, I've got to turn my plot on. Okay, and then I'm going to graph it. Okay, so there it is on the graph. Okay, oh, and that's something else that I had typed in from last period. Let me get rid of it. Okay, so that's the same scatter plot that I have on my paper. It looks a teeny bit different because on my paper, on our graphs, you saw that, you know, the y-axis was really long compared to the x, so it's just a little distorted compared to this one, but it is the same exact graph. And think about it. See how on the x, it only goes to 12, so they literally make 12 little tick marks, but on the y, it's just solid because it's going all the way to 240, and I mean, do you really want to try to put 240 little marks? No. So that's why they do it like that. Okay, so now let's move on to today. So today we're going to be learning about exponential graphs functions and their characteristics. Well, what is the equation of an exponential function? Y equals? Right. Now, sometimes you may see them write it with parentheses around the b. It's the same thing, though. You even may see them put a little dot for times in between them. It's all the same thing. Now, what did we say the x represents? The time. So for this scenario, it's the number of times we did it. What does the a represent? It was the start value. Okay, a is your start value. And then b is the growth or decay factor. Okay, now for this lab equation line, when we created this worksheet, the goal was for you to take your data that you turned into me, plot the points, put it in the calculator, do everything that I did, and then write the equation you got. But for time's sake, we just went with one set of data, the data I had, so you can just write that equation here. Okay, now, when you look at my graph, would you consider that a growth or a decay? A decay, because from left to right it's going down. The time is decreasing the more times I try. So it's a decay. Now, another way that you can know it's a decay without even having a graph to look at is you look at the b value. Okay, see how our b value is 0.81? If your b value is greater than 1, it's a growth. If your b value is between 0 and 1, it's a decay. And wasn't our value 0.81, which is between 0 and 1, which is why it was a decay? Now, it will never go below 0. Let's talk about why. Even if we had gotten really, really good at that, would we have ever had a time below 0? No. Not possible. Not possible. Okay? Yeah, it's never below. You're never going to have a negative time. Right, it'll never go below 0. So that's why it has to be between 0 and 1. It'll never be exactly 1. Let's talk about why. If we just, I'm going to pull this equation up for a second. Is this a growth or a decay? It's a growth because your b value is greater than 1. The b value is 2, which means it's doubling. So say that they're keeping track of like a mosquito population and it doubles. If it starts out with 10 mosquitoes, how many will it have the next time? 20, and then 40, and then 80, and then 160, and then 320. It doubles. Okay, so does it make sense to have a 1 there? No, a 1 is not growing or decaying, right? It's staying the same, because when you multiply something by 1, doesn't it stay the same? So that's why you'll never have a 1. It'll always either be greater than 1, which is a growth, or between 0 and 1, which is a decay. Now you may also be wondering where the 292 came from. So let's look back here. Remember a time where you had some points plotted on a graph and your teacher told you to draw the best fit line for the data? You tried to draw in a straight line that hit most of the data points. Well, you can also do that with an exponential curve. You just draw a curve, and it's really hard to do. Okay? But anyway, well, you can't hit them all, but you just do your best. So do you see if we extended the y-axis that it's going to hit way up here at about 292? Your a is your start value, which is also your y-intercept. Okay, think about it. In y equals mx plus b, when you plot your b on the y-axis, isn't that the starting value for your line? Isn't that where your line starts? It's the same thing. When you plot your y-intercept, that's your starting value. Okay, that's always the a in the exponential. Okay, now let's go down bottom and try these four. Okay, number 1, what is the a value? You can write on these graphs. We're not going to use them. What is the a value? 4. What is the b value? So is this a growth or a decay? Decay, because 0.2 is in between 0 and 1, right? So this graph is going to be going down from left to right. Okay, what about number 2? What's the A value? 2. So the start value is 2. So that means the y-intercept is going to be 2. What's the B value? 1/2. And is it a growth or decay? Decay. Okay, it's between 0 and 1. Number 3, what's your A value? What's your B value? Is it growth or decay? Growth. Because your B value is greater than 1. Okay, number 4, what's your A value? 4, what's your B value? And is it growth or decay? It goes up from left to right. Now, let's compare these two. This is an unrealistic example because no bank account pays any interest even near this. But say these two were representative of a bank account. Your start value is the same for both. Which account would you want your money in? Right, this one, because basically this one your money's quadrupling. This one your money's only doubling. So like on a graph, this one is going to start at the same place, but it's going to shoot up a lot faster than this one. Okay? Alright, now let's go to the next page. Just like lines and parabolas and ellipses and hyperbolas, exponential graphs can also shift. They can shift up and down. They can shift left and right. Okay, so let me graph one and show you. Say we have y equals, so we have y equals 2 times 2 to the x power. So our a is 2, our b is 2. It's doubling. Start value of 2. Let's graph it and see what happens. Wrong graph. Zoom 6. Okay, see how since the a value was 2, your start value, your y-intercept is right there at 2. And then the graph is doubling. It's going up. It's a growth. Let's look at what happens if we use almost the same equation, but then on the end we put a plus 3. What happened? It went up 3 units, right? So when they say plus k, that's up k units, right? So when they say minus k, what would that be? Down k units. Okay, well, do you see the difference between this one that says plus k and this one down here that says plus k? In this one, the k is not a part of the exponent, right? In this one, the k is a part of the exponent. Any idea which way this is going to shift? Which way, though? Left. Okay, remember when you were doing parabolas and you had like y equals 2 times x minus 4 squared plus 7? Yes, this would mean up 7, but this meant right 4, correct? The number with the x always is the opposite of what you would think. Minus is actually right, plus is actually left. So this one would be right k units. Okay, so now what we're going to do down here is we're going to graph this by just, they gave us the equation and nothing more. We're going to graph it. Okay, back when you learned how to graph linear, it was pretty easy. You looked at the b, that was your y-intercept, and then the m told you your rise over run, correct? Well, for this, you can look at your a and your b. Okay, what is the a? Okay, remember, the equation is y equals a times b to the x. So b is always the number raised to the x. So in this case, b would be 2. So where's a? Okay, think about it. If you put a 0 right here, isn't everything going to cancel out? So what does it have to be? A 1. Okay, so, but that still doesn't tell us enough. It does tell us something. It tells us that our starting point's at 1, and it tells us it's going to go which way? Up from left to right, because it's a growth. But we don't have any idea like if it's going to go up right here or up out here. To get that exact location, we're going to do a table of values, an XY chart. Okay, now, you're able to pick your own x values. You can pick whatever numbers you want. However, you need to keep some things in mind. Our x-axis on this graph only goes right 10 and left 10, so you definitely wouldn't want to be picking x values that are already off the axis. And also keep in mind that if you pick large x values that fit on here, does that necessarily mean the y's are? No. So for that reason, we're going to pick small numbers like -3, -2, -1, 0, 1, 2, and 3. You'll also notice that I picked a combination of negative x values and positive so that I can see what the graph looks like over here and over here. Any ideas now that I've given you x values to use how you can find the y values? If you have an equation and they give you a table with all x values, you just plug them in. So like 2 to the x power, what is my first x value? Okay, so type in 2 to the -3. No, just calculate it. 0.125. Any idea why the calculator spit out 0.125? Okay, well let's look. Let's go back to yesterday. 2 to the -3. How can you rewrite this so that the exponent will no longer be negative? Right, 1 over 2 cubed. Well, what is 2 cubed? 8. What is 1 over 8? Y'all divide it. 1 divided by 8. 0.125. That's how the calculator got that. They did all of this in the calculator. So now, to find the next y value, you're just going to replace the x with a -2. So type that in and see what you get. 0.25. Now replace it with a -1 and see what you get. Okay, the rest of them you can probably do without a calculator. What is 2 to the 0 power? What's anything to the 0 power? 1. Think about it too. We already had that point plotted because we knew our a was 1, so that's our y-intercept. What about 2 to the first power? 2. 2 to the second power? And 2 to the third power? 8. Okay, so now what we've created for ourselves is 7 coordinates that we can plot over here. So I'm going to work backwards and start with the nicer ones first. 3, 8. How do I plot 3, 8? Over 3, up 8. Okay, how do I plot 2, 4? Go over 2, up 4. Okay, what about 1, 2? And then 0, 1 we already plotted. And how did we know to plot that there from the beginning? The what? The a value was 1, and that's your y-intercept. Okay, then -1.5. That would be left one on the x, and then where on the y? Wouldn't it just be halfway between 0 and 1? And then -2.25 would be left 2, and then even lower than this one, which is kind of hard to do in such a small space. And then -3.125 would be so close to the x-axis it almost looks like it's sitting on it, but it's not, because if it was, this number would be 0. Okay, so it's a teeny bit above. Okay, now, do you see as you approach the negative side, like -1, -2, -3, they're all approaching the what? The x-axis, which is 0, right? Aren't all of these numbers getting smaller and smaller, approaching 0? Do you think that if you kept going further, like -4, -5, -6, do you think it's going to start to drop below and go into the negatives?
No.
It will not. Why will it not? Well, right. And whenever you have a graph that approaches somewhere but never crosses or touches, it's called a what? It's somewhere on this paper. Asymptote. Asymptote. Okay, y'all heard that before. An asymptote is like an invisible boundary, and the graph will approach it, but it will never cross it or touch it. Like if you plugged in -4, what will you get? Plug in 2 to the -4. Somebody plug in 2 to the -4, please. Okay, now somebody plug in 2 to the -5. Okay, now somebody plug in 2 to the negative 6. See how it's getting smaller and smaller? It's approaching 0. Okay? It'll get so small that your calculator will actually give you the answer in scientific notation because there's just that many zeros. 0.0000. So it'll write it in scientific notation. Okay? Now that you have points plotted and you see where the asymptote is, you can sketch the curve. Okay, it's going up from left to right because it's a growth, and that's because the b value is greater than 1. It goes through the y-axis at 1 because of the a value being 1. And I already knew the asymptote before I ever graphed it. Plus 0 in the k place means the asymptote's at 0. So like had this been a plus 1, the whole graph would have shifted up 1 unit, putting the asymptote at 1. And we'll talk more about that Monday. Okay, now that we have the graph, we can look into the domain, the range, and the behavior. When you hear the word domain, what do you think about? Okay, well, yes, but of what? What axis? Domain is x-axis, okay? So the x-axis runs left to right. So they want to know on the x-axis, how far left does this exponential function go? Right, forever to the left, so negative infinity. How far to the right does it go? Positive infinity. Now that's confusing to some people because they kind of want to look at this and say, well, this is the farthest right. But we didn't plot every point there is. Try the 4 on this end. What is 2 to the 4th power? 16. So you could go over 4 up 16. And as it's going up, isn't it also slowly going right as well? So as you go up, you're also going right forever. Now, range refers to what? Up and down, the y-axis. Which one do we worry about first? The down, right? Because think about it. On the x-axis, we went left to right, the negative to the positive. So aren't we going to do the same on the y, down, up, negative to positive? Okay, well, how far down the y-axis will this exponential curve get? 0. There's an asymptote keeping it from going below 0. Okay, right? It won't actually touch 0, but we're just going to write it because if you want to write the alternative, it's impossible. You can never write the smallest number there is. Okay? Right. Now, how high up can it go? Infinity, because it goes up forever. Now, when they ask for behavior, they want to know if it's increasing or decreasing. Increasing. Okay, what's your question? Right, like it's at 0 because there's an asymptote at 0, so it can never go below 0. It only goes from 0 and up. Yes, the asymptote controls where well, yes, it'll always go from the asymptote up forever. Okay, now, whenever they're asking about intervals of increase and decrease, and they want to know, like, where is it increasing, they care about x values. Well, haven't we already done the x values? So it's increasing from negative infinity to positive infinity. Think about it. Didn't it start increasing way over here? And then it continued increasing forever? So that's negative infinity to positive infinity. Okay, write that down and then we'll try number 2. Alright, number 2. What's your a value? What's your b value? Okay, so is this a growth or a decay? A decay. So we already know our graph's going to look like this. It's going to go down from left to right. Where's it going to cross the y-axis? 1. Your a value is your y-intercept. So you can go and plot that. Now, so we know 2 things about it. We know where it crosses the y-axis, and we know it's going to be going down. So we could do a rough sketch. We also already know where the asymptote is. Where's the asymptote? Is there anything out here in the k? Isn't this technically like plus 0? So the asymptote I already know is right here without even graphing it. But to get the rest of my points, what do I need to do? Right, the table. Now, to save time, why don't we have the 2 rows that are closest to me y'all plug in negative 3, negative 2, and negative 1. And then the other 3 rows, y'all plug in 1, 2, and 3.